Okay, we're going to look at a couple more systems here. This one we'll go ahead and solve, and something interesting is going to happen. If you remember last time, we had a consistent system where we actually had one unique point as a solution, and that's often the case. But the two we're going to look at today have different situations. So if you notice this, there's my three equations, three unknowns. The problem is they're not in the correct order, and we haven't seen this before, but just like with two equations, two unknowns, you have to have them in order. X, Y, Z equals a number, and then the next one, X, Y, Z, and so on. So I've rewritten it in the correct order here. So an easy step, but an important step so that you have everything in columns. Okay, now we're ready to go. So as you recall, we want to eliminate variables down below. And this isn't important, but just for talking purposes, let's label these equation 1, 2, and 3. So pretty much I'm going to go ahead and start with 1 and 3 because looking at this, I can easily see that if I multiply this one by 2, I'm going to get a 4x, and then if I added that to this minus 4x, that's going to cancel. So what I want to do here is go ahead and take equation 1, multiply it by 2, and then add it to equation 3, and that'll give me a new equation 3. So let's do that. All right, so I got to multiply 2 by everything here, so that's 4x minus 2y plus 6z equals 16. And I'm going to go ahead and add this to equation 3. Okay, and here's the interesting thing. 0, 0, 0. Everything cancels out there. But over on this side, I have 21. Okay, 0 can never equal 21. We've seen this kind of thing in two equations, two unknowns. This is not possible, so that means nothing can make this work. So that means no solution. Or if you want to write it another way, it's an inconsistent system. So what we have here are possibly 3 planes, or imagine 3 playing cards that are parallel to each other, but they never cross. So this is how they look, and you're just looking for that. And again, it's just like two equations, two unknowns. Now, I have one more problem here we're going to look at. Okay, this one, and we're going to start here. This one is going to wind up being the third case where we have infinite solutions. Okay, so we had one solution last time. The one I just did, we had no solutions. Now we're going to have infinite solutions. But it's going to wind up being a little bit different from two equations, two unknowns. So let's take a look at this. I don't have to rearrange this. I could go ahead, and this is a great equation here for multiplying by various things and getting rid of the x's. So I could actually have my x, y, z down here, and maybe a y, z here, and a z up here. That's fine, but just to make it less confusing for me, I'm going to go ahead and rearrange the order of these because I just want to see X, Y, Z, then maybe Y, Z, and then maybe Z that way. But again, it doesn't matter. It just looks better to me. Okay, so let's look at this. I'm going to start eliminating variables here. So I would like a new equation here without X. So that would mean if I multiply this one by minus 5 and add it to this, then the X's would go away. So what I'm wanting to do is take equation 1, multiply it by a minus 5, and then add it to equation 2. So let's see what we get here. So minus 5 times all of these, minus 5x, minus 5 times a minus 1 is a plus 5y, and minus 5 times 2, that's minus 10z, and then that equals minus 2 times minus 5, that's a plus 10. Okay. We're going to add it to this. Okay. So let's add them up. And the x's cancel, that's what we were hoping for. Minus 7 plus 5, that's minus 2y's. 12 minus 10, that's 2z's. And over here, 10 minus 8 is 2. And then what I could do here, just to make my new equation 2 a little easier, would be to divide everything by 2. So minus y plus z equals 1. So that's my new equation 2. We'll put them all in there in a minute. Now let's take a look at 3. What I would like to do for 3 is eliminate this x. Well, that looks pretty easy. What I want to do here is just multiply by a minus 1. So I'm going to take equation 1, multiply it by a minus 1, and then add it to equation 3 to get a new equation 3. So change all the signs here. So changing signs is the same as multiplying by minus 1. Add it to this one. Okay, and what do I get here? I get 0 equals 0. What that means is there are infinite solutions here, and that's fine, but we can't just state infinite solutions. When it was 2 equations, 2 unknowns, you could, because you knew what the line was. Each equation was the equation of a line, and all the points lied on that line. But where is the line here that creates the infinite solutions? Or is it all of the cards laying on top of each other that does it? We need to go further here. In a case like this, we're kind of stuck. I've got this equation here. And then I've really got this equation. And then I don't get any other equations because when I try and eliminate the x here, everything drops out. So what it really means is we have two equations that are kind of working together here. So these are the only two equations I can get. Okay, again, I didn't get anything here, it bombed out, but I know I have infinite solutions. Well, what you do in a case like this is, since these are my two equations, and I can't solve any further and get a number for z, I have to assign a number myself, like n or p or something. So what you do here is you say, okay, we'll use p. P stands for any number. So any number I put in for z is a value for z. So let's go ahead and let's get that here. So I can have any number for p, but I can't have any number for x or y, only certain ones. So if z equals p, if I put that particular number in here and solve for y, okay, if I want to subtract p over here, and then again to solve for y I need a positive here, so I need to multiply through by negative. So for any number p, y has to be p minus 1. So that would be the number here. And then finally, what is x? Well, go to the first equation. X equals minus y, which is here, plus 2z, and z is going to be p. So again, for any number p, I'm going to get the x value that goes along with that. So minus p plus 1 plus 2p. So 2p minus p, that's just p plus 1. So that's here. So that's what the solution looks like, and this is how a particular point looks, but it represents infinite amount of points. So for example, p equals 3. 3 minus 1 is 2. 3 plus 1 is 4. That's a point that satisfies all three of these. What if p equals 7? 7 minus 1 is 6. 7 plus 1 is 8. So you get the idea. This represents all of the points that satisfy all three of these equations. And again, the reason that we assigned a generic number to z and then solve for y and x is when you get a situation like this. So it is a consistent solution, you just have infinite solutions. Okay, on the final part of this chapter, or this section, 6.2, I'm going to do an application problem. That'll be next time. But the interesting thing about it is, so far everything we've seen is three equations with three unknowns, and you have to have that. But sometimes an unknown might be missing. So you might have three equations, but maybe x is missing here and z is missing here. So this particular word problem is going to show that and kind of how to think your way through it. But it's really exactly the same thing. It's just using elimination over and over so that you can get to those variables and either assign them numbers, like we did on the last one, or assign a parameter like z equals p and then come up with your set of points that way. Okay, some good examples in the book too. This stuff is a little bit confusing, but hopefully these examples help.